Hi everyone, welcome to this agentic version of myself. Periodically, I will try to talk through some technical problem I am working on. This video is a quick demo at using HAgent with Gemini for chip design. At the end, I'll share a few open questions and my own take on things. HAgent and Gemini will be extending a simple RISC-V CPU called Dino with the RISC-V B extension. It's the kind of project that would take most undergrads and even grad students quite a bit of time. Here, HAgent is just helping with the compilation of the RISC-V project.
Okay, I'm replaying the recording that I did in which Gemini works. So the first thing we do is clone the HAgent repo. After I have cloned the HAgent repo, you have to synchronize to get all the packages. And what I'm gonna do is just create a sample. And for this, we have a script inside HAgent, so it's easy to create a sample and using Dino CPU. What this does is create repo directory in which you have some code. You also, for example, the pipeline CPU, there are two CPUs, the pipeline, dual issue, non-pipeline Dino. And the options to compile are in the HAgent.yaml, that this is something that HAgent reads. Then what it creates is the HAgent server that we can, it's just this script you need to add the MCP to things like Gemini. The same thing works also with Cloud Code. So you just do MCP add, and then you have the server added and configure for the current directory and the setup and everything. Then you can start Gemini, and then you can say, can you recompile the CPU? And then it starts to recompile. This is using HAgent. So as you notice here, it's saying the HAgent port. It's recompile HAgent. I have accelerated a little bit because it takes like 2 minutes to recompile the CPU. But then the important thing I ask is, can you, doesn't have to respect, can you add it? And then this is starting with Gemini itself. It's not help for the moment with HAgent. It reads the files, tries to decide to do the changes, and then it does the code generation, and then at the end it's going to call HAgent again to recompile. If it works on compiler errors, it's going to go back and iterate, fix it, but this time it did it correctly, no type errors. So finish, and when it finishes, it create the code. This has been accelerated, but it did it in like in 4 or 5 minutes. And you can look at the code, and one thing that is, it works, but it's not great. Why it's not great? If you look at the bottom, the operations, so bit encoding are added at the case statement default. And that's the code, and that's sort of the end. But again, if you look at the code, the operations are in the case statement, which is not ideal for performance. So what we're gonna do on the part 2 of this demo is how to fix this.
So in the first part, we saw that Gemini with HAgent was able to compile and modify Dino to add the RISC-V B extension. It worked, but the code quality wasn't great. The issue is that Chisel used 5-bit opcodes for the B extension, while the original opcodes used 4. That mismatch led to a case statement that isn't fully parallel. It runs, but it's not ideal for performance. This second part of the demo shows how to fix it.
So in this second part, it's also a screencast recording. We can see in the Scala LU. Well, then that's not the path. The path was, I forgot at the time where was the path. So Scala LU, you notice for the normal operations use LU dot, but for the some of the new operations is use IO dot operation, and this creates some complication on the behavior on the code. So the result is that in the generated code, you look at the bottom, this part of the case statement is most of the RISC-V B extension. So I forgot to save the context, so I had to start from scratch. It's just This is the generated block. This is due to issues on the Scala. Please fix it. And I accelerated the compile and edits. As you can see, the seconds go very fast, but I didn't do anything. It was all fully automatic, starting with that feedback that I provide to Gemini. Then it tries something and it checks the code and it didn't work correctly. One thing is interesting is that there are two ways to compile the CPU, single CPU with debug or without debug. And in the first version, it generated with no debug, but now it's generating with debug. But after it figures out what's the issue, it iterates, it fixes it again. It checks by itself, but every time it's calling HAgent to recompile. When it verifies the implementation, it checks that the code looked correct, so we exit, and we can check the LU, and then it's like, oh, I did a non-debug. That's the original. So this is the non-debug and debug. The debug, the non-debug is the one it did in the first session. Now it did it with debug information, so there is going to be more source codes annotations. That's why they have all this code in text. But you notice there's a single case statement, and the code is changed, and that's it.
To conclude with my academic avatar, there are open questions with this flow. For example, it's unclear what the best way is to integrate MCPs. In this demo, I used a HAgent build MCP, but the code quality improvements were done manually. Other MCPs, like a verification regression MCP, could also play an important role. My view is that we're going to go through a phase of MCP experimentation. Over time, as base platforms like Gemini, Codex, or Claude Code continue to improve, the boundary of what MCPs need to handle will shift. I hope you enjoyed the demo. Remember, HAgent is free to download from GitHub. It's still under active research and development, so don't expect production quality just yet. But if you have pull requests or fixes, we'd love to see them.